Alright, hello guys. So today we have a pretty simple proof. Basically, we can imagine two sequences. We have an, which converges to the value a, and we have the sequence bn, which converges to the value of b as n goes to infinity. And now we're trying to prove that the sequence cn, which just equals to an plus bn, so c1 is a1 plus b1, c2 is a2 plus b2. Basically, this sequence converges to the value a plus b as n goes to infinity, which kind of makes sense, like intuitively. Like, I don't know, what else it converge to. However, this is analysis, so we low-key have to prove it. So basically, what we have to show is that for every epsilon greater than 0, there exists an n from the natural numbers such that for every n greater than that n, we get that Cn minus C is less than epsilon, where C is the limit of our sequence, and we said that C equals A plus B. Basically, that's the limit, and Cn, just equals An plus Bn. So we have to show that this holds. And basically, how do we show that? Well, we can start with by looking at this kind of error function, Cn minus C. And we can basically say that this equals to, well, what does this equal to? We know that Cn just equals to An plus Bn, and we know that C just equals to A plus B. So this is the same as saying this, and now we can rearrange this around so that we can basically have the absolute value of An minus A plus Bn minus B. So we can write this. And now, using the inequality, I think it has a name, kind of forgot what it is. But, the very useful inequality, A plus B is less than or equal to the absolute value of A plus the absolute value of B. This is a very classic inequality. In analysis, you use it all the time. For example, like 5 plus -4, the absolute value of that just equals 1. But this is obviously less than the absolute value of 5 plus the absolute value of -4, which equals to 9. So here basically even if a number is negative, this part still makes it positive. So this will always be greater than or equal to. They're both positive, then it's just equal to. So basically we can use that here. So we can say that this is less than or equal to An minus A plus the absolute value of Bn minus B. So we got this far, and now we're basically trying to how do we decide what this value and this value is. Well, if we remember, An and Bn are sequences that both converge to a real value. It's important to say it's a real value because it can be infinity or negative infinity, because with infinities things get a little bit more interesting. But yeah, basically we know that these sequences converge, so that we know so we know that this definition holds. We know that for every epsilon greater than 0, there exists an n from the natural numbers, such that for every n greater than n, An minus A is less than epsilon, and we can say the same for Bn. But basically, so wait, I'm just put this on the side. The n's can differ though. So for this one, we can say that there exists an n. We can call it Na, such that for every n greater than Na, we have that An minus A is less than epsilon over 2. Epsilon can be whatever. It can be any digit that's greater than 0. So the epsilon we can choose right now is epsilon over 2. And for Bn again, we can say that there exists an Mb such that for every n greater than Mb, Bn minus B is less than epsilon over 2. Now, because we basically have an Na and an Mb, where after those values, these two conditions hold. So now the trick is that we can choose an n which equals the maximum value between Na and Mb. So this just makes sure that basically any n that's greater than this n basically is going to be greater than Na, and it's going to be greater than Nb, so that both of these conditions hold. Basically we know that both of these conditions here are going to hold now. So now basically after this n, we see that Cn minus C is going to be less than or equal to epsilon over 2 plus epsilon over 2. So basically less than or equal to epsilon. And then boom, we proved that. we show that for every epsilon, and epsilon is whatever we choose. So this works for every epsilon greater than 0. Here we could also choose epsilon, like, instead of epsilon over 2, we could choose epsilon over 10. It doesn't matter. This is just, so it kind of works out nicely at the end. But basically, we show that for every epsilon greater than 0, there exists an n from the natural numbers, which is this n over here, such that for every n greater than that n, we have that Cn minus C is less than epsilon. So basically, with our assumption that the limit to Cn is a plus b was valid, we showed that the definition holds. So basically, we show that, so basically we proved the statement. And it's a pretty intuitive statement. It gets a bit more cool and tricky to use it for multiplication. For example, if an converges to a and bn converges to b, then if we say that cn equals an times bn, we can say that the limit, so the limit as n goes to infinity of cn equals just a times b, which again makes sense, but it's a bit cooler to prove. So I can do a proof of that like next time, because it's not it's not as straightforward as here, but it's still pretty straightforward. So if anyone wants the proof for that, but yeah, that's basically it. Pretty solid classic proof. Don't really know why we need it, but now you know.